Today's video brought to you by Lego Blacktron, the arch enemy of Mtron. So in 5.4, we're going to look at properties of logarithms. They're fairly similar to the properties of exponents. Remember that these things are inverses of each other. First, let's recall that if y equals b to the x, nope, that's not the letters we used. If y equals a to the x, no, it was for b to the k equals a. That's true if and only if log base b of a equals k. That was our connection between exponential versions and logarithmic versions. And you recall back in 5.2 or 5.1, we had all those properties of exponents that said we could add the same bases, etc., etc. So now we look at similar properties of logarithms. So if we have a product of two things within the logarithm, by the way, notice we've now changed the log base b to log base a. This is related to if you have b to the x times b to the y, we simply add together the two exponents. Recall that a logarithm is an exponent. And this one is related to if we have b to the x raised to the y power, we simply multiply the two exponents together. So here's an exponent. This entire thing is an exponent. It should stand to reason then that an exponent times an exponent follows our general properties of exponents. And then this one was if we had, let's say, b to the x divided by b to the y, provided b was not equal to 0, we did all this. And then this is just a change of base formula that we had that's not super useful anymore, but we might have needed it for a calculator back in the day. And then some other basic properties. Log base a of a equals 1, log base a of 1 equals 0, regardless of what that base is. And then this is directly connected to the fact that logarithms and exponentials are inverses of each other. So what we're going to do is we're going to look at ways we can use these properties to manipulate expressions. I tend to think about this left side as condensed expressions, meaning there's a single logarithm, and this right side as expanded logarithms, and it's sums and differences. And sometimes you'll see a language, I think my math lab uses this, condense these expressions into this, or expand expressions in this form into that. So here's our first example. I got log base 3 of 81 times 27. We are to express them in terms of sums and differences. Well, because there's a product within a logarithm, we can use that product property and write this as log base 81. Notice it becomes plus log base 3 of 27. That's because of this property right here. For multiplying things within a logarithm, we can separate them. Well, then I know from my expression b to the k equals a implies log base b of a equals k. I know that this is 3 to what power equals 81, so I know that's 4. And I know that this is 3 to what power equals 27, so I know this is actually 3. So the answer to this thing is really just 7, if we wanted to simplify it all the way out. And we could, because these were nice, neat logarithms, we could do all that by hand. This next one, notice we got letters everywhere, so we can't do that. All we can do here is take that product of 8 times g, by the way, it's implied that this is what's happened, and take log base t of 8 and add it to log base t of g, and that's it. That's all we can do to that one. Likewise, this is log base e. It's a product of two things, so we can rewrite this as a sum of the values in the logarithm. All right, so here's another whole monster page of the same thing, where we are taking a condensed version of a logarithmic expression, and we're expanding it. So here, when we have an exponent within a logarithmic expression, we simply multiply it by it, and we're done. That's expanded. Same thing here. Note this is log base e, so this just becomes natural log, 5 times natural log of y. Same thing here. It doesn't matter that there's a negative out there. It just becomes negative 8 times log base b of q. I'm not consistent when I'm writing parentheses, so I guess we should be careful. This next one's a little bit tricky. Note that we can think of this as a to the 1/3 power. So the cubed root of a value is actually an exponent. Once you see that it's an exponent, just now multiply by that exponent. Okay, so these are all applications of that. If you have an exponent, multiply by it within the expression. Here, when you have division, you would divide by the you would subtract by the divisor. Now remember that division, the order you subtract matters, so we have to subtract this divisor. That's the one that needs the negative. Then when we look at the last things in our expression, we note, hey, we can still expand this one a little further. We can write that as multiplication. And we have to be careful, it's only times this piece right here, and since we're already subtracting it, it just becomes minus 3 log t of x. Okay, here's another one that has 3 things multiplied together. That's fine. It just means we have a sum of 3 different individual logarithmic expressions. Note that our last one has an exponent in it, so we're going to multiply that. Oops, I forgot the plus sign here. So the final answer in expanded form is this. I should be boxing in all my solutions here so you can see when we're done. Okay, here we have division again. Note this is log base 10. And so we have log, often called common log, minus common log of m to the 9. And these are both exponents within a logarithm. So we multiply each of these logarithms by those respective exponents. And we're done. That's it. Okay, the last two are a little bit tricky. And that we could take care of the radical right off the bat, or we could apply the radical within. So the first one, I'm going to rewrite this as log base a of x to the 6 over p to the 5th raised to the 1/2 power. And then I'm going to multiply that by that 1/2 and go here. On the next one, I'm going to do simplifying first. Doesn't matter which way you do it, just that you do it correctly. Okay, so with this, note this 1/2 is times this entire logarithm. So I could think about this as brackets around this, and then inside I'm going to manipulate / expand these things. So I'm going to have 1/2 times bracket log a of x to the 6th power minus log a of p to the 5th power because of the division. We subtract the divisor. Well, then note we've got these exponents, so we just multiply by them. So we'll do 1/2 times 6 log a of x minus 5 log a of p. Why did I put parentheses? There we go. That could be our final answer. Or what my math lab is going to want you to write, distribute the 1/2 through the brackets. So 6 divided by 2 is 3. And 5 divided by 2 is 5 divided by 2, or 2.5, whichever way you want it. And that's really probably the cleaner answer. All right. On this one, I said I was going to simplify within the radical first. So before I even note that the cubed root of this is raised to the 1/3 power, I'll do my properties of exponents. A to the 6th divided by a cubed is really a to the 3rd. And b to the 5th divided by b to the 8th is really b cubed in the denominator. And then because of the radical, I'm going to do all this to the 1/3 power. So instead of applying properties of logarithms like I did here, I applied properties of exponents within here, simplified that expression. And now I'm going to do precisely what I did over here. Actually, no, I'm not. Now I'm going to do another property of logarithm that says when you have an exponent on the outside, you multiply. So log base a of a to the 3rd to the 1/3 is really 3 times 1/3, which is just a. And b to the 3rd to the 1/3 is really 3 times 1/3, or just b. And our final answer then is just the difference of these two logarithms. Just kidding, that's not our final answer. Oops, I need to leave that as an a. There's one last thing we can do. Notice this base and this thing within the logarithm are the same, so that is exactly 1. Now we have our final answer.